Hi students. Hopefully if you're watching this video, you've already watched basic bonding patterns, the video I had earlier, which followed the octet rule. In this particular video, I'm going to continue with bonding patterns, but I'm going to discuss when you have a central atom that's in the third energy level or beyond. So if it has a quantum number, principal quantum number, or 3 or beyond, and it's typically found in the non-metal region, what can happen? So basically, this is bonding patterns for expanded octets. So like in the last video you watched, we focused on elements in the second energy level. So we were looking at carbon, nitrogen, oxygen, fluorine, and we were discussing bonding patterns. And we saw that carbon, and this is why carbon is such a common central atom. Carbon likes to form 4 bonds because it has 4 valence electrons. That's why there's 4 dots, it's group 4A, but it wants 8 to be like neon to have a stable valence shell because that S and P sublevel are filled. And if I look at nitrogen, which is 5A, it has 5 of the dots and it wants to be like neon, so it needs 3 more, so it actually forms 3 bonds. And group 6A, 6 dots, needs 2 more electrons, so it forms 2 bonds, right? The additional electrons would be here, maybe from a hydrogen. And then they would be stable and happy. Well, when you're in the third principal energy level, let's not forget that the valence shell is really what we're looking at when we're discussing bonding. So we don't care about the core electron. So if I'm in principal energy level 3, those are the first electrons that are involved in bonds. So it doesn't matter how many are in the second or the first. Now, that's one of the nice things about group numbers. When we look at the principal energy level 3, it doesn't matter, whether I'm a phosphorus or a nitrogen. I'm in group 5A because I have 5 valence electrons, right? So I basically have a 3s2, 3p3 configuration. So phosphorus, just like nitrogen, it wants an octet, and it wants to be like argon over here. But so what will it do to get an octet? Well, it has 5 valence electrons. It likes to form 3 bonds as well. If I look at sulfur, right, it's group 6A. It likes to have 8 valence electrons, so it tends to form 2 bonds and has 2 lone pairs, just like oxygen. And chlorine, like fluorine, likes to form 1 bond, so like in hydrochloric acid, and 3 lone pairs. But something else happens when you get to the third energy level, and that's really what this video is about. So when you get to the third energy level, you see what's termed hypervalency. You see an expansion of the octet. So what do I mean? Well, again, if I have principal energy level 3, like phosphorus, sulfur, and chlorine, those particular elements, because they're in the third energy level, they don't just have an S and P sublevel, which is the octet, they also have the D sublevel. And that D sublevel, if you remember, has 5 orbitals, so it allows them to expand beyond the octet. So you end up getting sometimes more than an octet, 10 or 12 electrons around a central atom in hypervalency. Now, if you look at a periodic table, this is primarily happening in the non-metal regions. This is not going to, we're not really going to discuss the metals too much because we're looking primarily for covalent bonding right now. But I do want to point that out. But with this hypervalency, we start seeing bonding patterns. So, like we said before, if we're only getting an octet, we see the bonding pattern for group 5A, nitrogen and phosphorus. They have 5 valence electrons. We can see 3 bonds and 1 lone pair. But because phosphorus is in the third energy level, we can actually expand the octet And in some cases, you'll actually see 5 bonds, which makes sense because this is group 5A. Now, if I go to sulfur, if as the central atom it only needs to attach 2 things, it'll form an octet, just like oxygen, 2 bonds, 2 lone pairs. But sometimes it needs to have more atoms attached to it. So in that case, you can expand the octet and have 4 bonds and 1 lone pair. Or if you really need to, it can have 6 bonds. And if you look at that, that makes sense because this is group 6A. And if I have 6 bonds, I have a hypervalency of 12 electrons. If I have 5 bonds, I have a hypervalency of 10 electrons. So the pattern for group 5A is 5 bonds or 3 bonds and the 1 lone pair. For group 6A, it's 6 bonds, or what we see here, 4 bonds and 1 lone pair, or 2 bonds and 2 lone pairs. So you see that it's always being, deducted by 2 bonds because the 2 bonds can be replaced with a lone pair. So 5 bonds or 3 bonds and 1 lone pair, 6 bonds or 4 bonds and 1 lone pair, or 2 bonds and 2 lone pairs. So now let's get really hypervalent and let's look at group 7A, chlorine in the 3rd energy level. And again, we can expand the octet. Does it mean it always does? No, sometimes it just forms 1 bond and 3 lone pairs, and that's an octet. But in other cases, it might form 3 bonds and 2 lone pairs. So in this case, it has 1 bond, 3 lone pairs. Here it has 3 bonds, 2 lone pairs. And sometimes it can form 5 bonds and 1 lone pair. And don't forget, this is group 7A. And in this case, it's going beyond 10 or 12. It actually ends up having 7 bonds and no lone pairs. And in this case, the hypervalency is 14 electrons. But for the most part, the rest of these have 10 or 12, right? So you have 2, 4, 6, 8, 10, 12, 2, 4, 6, 8, 10, 2, 4, 6, 8, just the octet, right? 2, 4, 6, 8, 10, 12. For the sulfur right here, 2, 4, 6, 8, 12, or 10, 2, 4, 6, 8, 10, 2, 4, 6, 8. The other pattern you can see is group 7A, 7 bonds, subtract 2, 5 bonds, 1 lone pair, subtract another 2, 3 bonds, 2 lone pairs, and subtract another 2, 1 bond, 3 lone pairs. But nothing serves best as an example. So let's focus strictly on the 5A. So we could see what we said earlier. If I'm just following the octet rule, I might have 3 bonds like I do in phosphine. And if I look at phosphine, it has an octet around phosphorus. Now, in some cases, right, I might actually have more than just 3 bonds. Remember, this is group 5A. So phosphorus can have 5 bonds. And I'm just going to erase this for a second. And if I do that, you could think of it as 1, 2, 3, 4, 5. And an example for that would be my PCl5, phosphorus pentachloride. And that would look like this as a Lewis dot. Now, I'm not doing the lone pairs around the chlorines, but just to show you the basic configuration. But we see that phosphorus has five bonds. Now, the other interesting thing you'll notice is a lot of times it doesn't have to have five atoms attached to it to have five bonds, like in the case, and I'll show you right here, right? So here I have my five valence electrons, 1, 2, 3, 4, 5. Guess where it does this? Your phosphate. It's only got four oxygens attached, but one of the oxygen has, it's called a pi bond, or we can just think of it as a double bond, an additional bond. So those are the bonding patterns of 5A. 3 bonds, like in the case of phosphine, or 5 bonds, like in the case of phosphorus pentachloride or phosphate. Now let's go to 6A. Again, sulfur is in group 3, or sorry, principal quantum number 3, but it can be happy just having an octet. So it has 6 valence electrons, but it wants 8. So it might do what? Form 2 bonds with hydrogen, and we see that with hydrosulfuric acid. Or it might say, you know what? I'm going to form 4 bonds. So where might you see that? Well, you might see that in SF4, and in SF4, I'm not drawing the lone pairs on the outer atoms. That's another video. But there we have 4 bonds in 1 lone pair. But remember, this is group 6A. So I can actually have 6 bonds. 1, 2, 3, 4, 5, 6. Like in the case of sulfur hexafluoride. So you can see that this is an expansion of 12 hypervalency. This is an expansion of 10 hypervalency. So these are bonding patterns. So group 6A, what does it like to have? 6 bonds, or 4 bonds in 1 lone pair, or 2 bonds in 1 lone pair. Oh, I was going to go back to 5, but you get it. So now if we go to 7A and we're expanding, right? Third energy level. So the first thing that I might like to have, if I just want an octet, 1 bond. Where do I see that? I already did hydrochloric acid. I thought I'd do something else. What about this polyatomic oxyanion? Isn't this hypochlorite? Well, that would be 1 bond. What if I wanted 3 bonds? Well, what would that be? Well, there's an example right there. And what is that? How about your chloride ion? Right? So now we're going to multiples of 2, right? So 1 bond. This is 3 bonds. What do you think the next one's going to be? It's going to be 5 bonds. 1, 2, 3, 4, 5, and 1 lone pair, of course. So what does that mean? Well, where might we see that? Oh, you mean the oxyanion chlorate? And then don't forget, this is group 7A. So it can go even beyond the 10 and 12 hypervalency that we tend to mostly see, and even go up to 14. And when does it do that? When the group 7A central atom has 7 bonds, like in the case of, oh, what's this? ClO4 minus. Oh, that's my perchlorate oxyanion. And you see that the oxygen, it likes to have two bonds. This one only has one. So if I put another bond here and do that, oh, that's my perchloric acid. And that's why perchloric acid only has one proton, because only one of the oxygens isn't double bound to the chlorine. And that has to do with formal charges and other things, which the next videos we'll talk about. But basically what I see is the bonding pattern for this is 7 bonds. So group 7A, 7 bonds, or 5 bonds, 1 lone pair, 3 bonds, 2 lone pairs, or if I just want the octet, 1 bond and 3 lone pairs. So the whole point of this video is you can use Lewis dots to help you recognize bonding patterns for central atoms in group 5A, 6A, and 7A that are beyond the third energy level and have that D sublevel, which allows them to expand the octet and reach what's referred to as hypervalency, which basically means they have more than 8. So I hope this video was helpful. Please watch the next videos as we move forward. And now we're going to apply these bonding patterns to Lewis dot structures and determining which are the preferred Lewis dot structures. Thanks for watching.